Okay, guys, can you guys hear me? You guys hear me?
Yeah.
Okay,
Yeah.
perfect.
Yeah.
Thank you, Josh. You know what? For the first lecture, let's give it 1 more minute while we're receiving more attendance. Okay? Always people have some problems logging into the system, especially for the first lecture. Let's give it 1 or 2 minutes. I think some parents are talking to me say they have some issue logging into the system. Okay, 2 more minutes. Yeah, 1 more minute while we're receiving more attendance. Okay? We're just going to get started in about 1 minute. Yeah, for the guys who have already in our WebEx, so please make sure you can have access to our microphone, because from time to time, our lecture needs a lot of interactions. If you want to ask me some questions, you can just unmute yourself, so therefore everyone can hear you. Okay? All right, it's 4:32. Let's get started. So welcome, guys. Welcome and bienvenue. Welcome to our lecture. And as a common practice for the first lecture, I always like to give you guys a little bit background information because we always have some new students. I like to give you some information telling guys like where we are and where we get started, so on and so forth. Give you guys some basic overview about lectures. So the background why we're having this lecture is because these days, due to the coronavirus, most of the school board are actually shutting down across Canada, right? So at least we can have like 2 weeks or even more than 2 weeks for the shutting down period. So after talking with different parents, we realize instead of like sitting at home, maybe we can take this opportunity to give us some boot camp focus, pretty much helping guys to enrich your, mathematics related topics, so on and so forth. That's pretty much where we come from for this bootcamp. And the reasoning why I choose number theory is because I realize number theory is kind of like an independent topic compared with the other of all the mathematics topics. For instance, if I want to choose the algebra, it means that you guys need to have a lot of pre-knowledge, let's say sequence. You have to learn a lot of pre-knowledge before you can actually go for the sequence. Or if I choose the trigonometry in Canada, you're pretty much going to learn it in grade 11 or in grade 10 or grade 12. It really depends on different provinces. So therefore, it might not be so straightforward for us to find a algebra topic which can be pretty much applicable across the board. So after some serious consideration, we decide to go for the number theory. There are actually 2 reasons behind that. The first reason is that number theory is actually a very important topic and also a very complicated topic. If you want to go to any kind of math competition, especially competitions from the states, like the AMC 8, 10, or 12, there will be a decent amount of area, like a decent amount of questions focused on the number theory. And if you want to go for like the high level math competition, like Canada, let's say the COMC, or like the Euclid, or some other Waterloo related math competitions, in the last few questions, you're still going to see a bunch of combinations, comprehensive questions combined with the number theory or the other topics in mathematics. So that being said, the number theory is actually a very important topic, and I like you guys to take this opportunity to have some further like in-depth understanding for the topic. This is actually the reason number 1. And the second reason is that even though the number theory is very important, unfortunately, none of our day schools is going to put too much efforts on the number theory, right? It's not actually in our regular curriculum. Our high school, not only in Ontario, but also in other provinces, it won't focus too much for the number theory. So that being said, you're going to have a gap between what you are learning in the day school and what you will be tested in a math competition, right? So that's pretty much the reasoning and like the rationale behind our lecture, why we like to choose this number theory in order to make sure you guys can take this opportunity, have some in-depth understanding or more systematic understanding how to learn the important concepts for the number theory. All right, that's pretty much a background. Second, what I want to talk about is pretty much the organization of our lecture. Our lecture is actually organized in a way that we're not only talking about problems. I know you guys, pretty much most of you guys has already been to different math courses, the summer schools. I think most of the summer schools is going to focus on like the problems. You practice one problem and then practice another problem, which is good. However, I believe that for something more important is that you need to understand the basic concepts. You need to understand the strategies to solve a problem. Like in Chinese, we say the fishing and fish. Which one is more important? Of course, fishing is more important. So that being said, the entire organization of our lecture goes in this way. For each lecture, I'm going to spend the first half of the lecture talking about the important concepts, the theorems, and some common strategies to solve the problem. And then after you guys already know these mechanisms, all those like guidelines, we're going to move on to some real problems. So these problems are actually selected from different levels of math competitions. Something can be easier, something can be more complicated, but nevertheless, all of the problems are actually targeted on the concepts that we introduced in the first session. This is kind of like a handshake between those two parts. You always have the concepts, and then you always have your problems to basically practice the concepts. Okay, that's pretty much, I think, for the first part, the background and organization of our lecture. And then we go to the second part of lecture is the language. About like 2-3 years ago, most of my lectures are actually bilingual. So when I say bilingual, I don't mean English and Chinese. I mean English and French, l'anglais et le français. But you know what, these days, because more and more, I actually focus my education pretty much in Ontario. So more and more students are no longer choose the French immersion. So that being said, the students in my lecture is no longer so capable speaking in French. So that's part of the reason actually drives my lecture is more from like a bilingual into unilanguage lecture. So, but I like to ask you guys at the very beginning, does any one of you guys speak French? Does anyone speak French in our lecture? Quelqu'un qui parle français
Yes.
ici?
Oui.
I speak a
C'est
little
qui?
bit.
C'est Lucy?
Oui.
C'est Ernst? D'autres personnes? Regarde, malheureusement, il n'y a pas de gens parler français ici. Unfortunately, we don't have a lot of persons speak French here. So no problem. So, this is how it works. If there's one person who does not speak a word of French, everyone, who does not speak a word of French, everyone will switch into English, right? Even though you work with the Quebec people, right? If everyone speaks French except one person, so everyone will speak into English. So not a big deal. But generally speaking, just give you a kind reminder. In Canada, French is very important. C'est très important pour quelqu'un de parler français like in Canada. En particulier, si vous avez la collaboration avec le gouvernement du Canada, le gouvernement du Québec, c'est très nécessaire pour moi de parler français. Especially from time to time, I have some collaborations with the government of Canada, the government of Quebec. So I have to deliver a public lecture in the Ministry of Education. In that case, le français est nécessaire. C'est obligation, right? I have to speak French. And also, as a kind reminder, I believe is that, you know what, if you guys want to go for the Euclid and COMC, this will be because you are still in a relatively lower grade, but eventually you might go to this kind of high-level math competition in Canada. You know that in this high-level math competition in Canada, because they are across the country, so English and French, they are all correct. So you can actually choose English to do the math, to do the work, or you can choose French to do the work. There are kind of like a little bit tricks. If you choose to do the work in French, most of the English teachers, they won't be able to mark your paper, right? So what's going to happen is they will forward your mark, all your papers, all the way to Quebec. The French-speaking teachers will be ready to mark your exam. So normally speaking, just based on the statistics, the French-speaking teachers are more, comme en français, gentils. In English is like more nice, it's more generous. So they will also like to promote the, like the French speaking community. So even like the same quality of your paper, if you write it in French, you end up getting a higher score. This is kind of like an extra hint, okay? And also, these days, there's like the coronavirus, there's a lot of problems. People want to call it Service Canada, Service du Canada. And if you choose English, it's probably going to take forever for you to get connected, right? Because there are a lot of people waiting in line. However, if you choose French, you'll be connected immediately. So with all those informations, what I'm trying to say that if you want to live in Canada for a relatively longer time, learn some French. It's actually pretty helpful for, for like from a long ways perspective. All right. After talking about the language, let's go for the format of our lecture. Normally speaking, my lecture contains two major formats. The first one is the live lecture, like the one what we are talking about at this moment. I'm here, I'm actually giving you the live presentation. If you have any questions, you can talk to me, interrupt me, so on and so forth, like the regular lecture you see, for the live lecture. Well, the other one is the pre-recorded lecture. Pre-recorded lecture is pretty much you watch the YouTube, right? The lecture has been pre-recorded. You can just read it. You can watch it unlimited times you like. Well, if you have some questions, you might not be able to get an answer on the spot. You need to contact me either using WeChat or like the message, like the Facebook message. But nevertheless, you're gonna listen, finish my lecture, and then contact me afterwards. Well, for this time, I actually advertise a new type of presentation, a new type of lecture. I call it a delayed live lecture. So this is the one what we are going to take it for this 10 lectures. So what is a delayed live lecture? So it's pretty much a combination between a live lecture and also a pre-recorded lecture. So this is how it works. So for the introduction parts, like what I'm doing currently, it's going to be a live introduction. I'll give you guys questions if you want to. I give you guys the concepts. If you want to have questions, ask me, so on and so forth. But as long as we go to the real content, like the beef and potatoes, I'm going to switch into a pre-recorded section. So the recorded section is I did before my previous lectures. But nevertheless, I will be here all the time. So I will be monitoring all the chat board. Make sure if you have any questions, you can ask me, and I will give you the answer in a real-time basis. And why I like to come up with such a solution, there are actually some reasoning behind it. And these days we have a lot of like students, they want to go to the university to do some either the internship or want to do some collaborations, so on and so forth. Especially these days, the trend is becoming younger and younger, right? Normally people go to the university, students go to the universities for their internship when they were grade 11 or grade 10. But these days, even grade 8, grade 9, they will find out these opportunities to go to the university. And sometimes they take some lectures from the university with the other students. So that being said is from an early age, we need to gradually understand how the university lecture works. I'd like to give a quick example. So if you guys in a regular school, in your high school area, pretty much the teacher is facing to limited students, I don't know, 10, 12, it depends on different regions, right? And then when the teacher is presenting the lecture, if you have any questions, you can just stop the teacher right away. The teacher will give you explanations. After all the problems has been cleared, the teacher will continue to the next section. Right? This is how it works for the high school territory. However, as long as I go to like the university territory, it doesn't work this way. The teacher will give a lecture based on my experience with. I actually went to McGill for my college education. So as long as like the teacher give a lecture for the students, the fresher sophomores, whatever, there will be like hundreds of students basically in the same lecture. So it is impossible for the students to ask the teacher on the fly and also impossible for the teacher to answer every single one's question on the fly. Otherwise, no one will be able to make the lecture continue, right? So normally how it works is that the teacher will continue for topic for, I don't know, 10 minutes, 15 minutes, and then he will stop from there. Ask you guys, for the last 15 minutes, does anybody have any questions? So on and so forth. So this is kind of like how it works. You need to hold your question for about maybe 5 minutes, 10 minutes, and then wait for the break time. Like the teacher will give you this break time and ask her for the questions. This is normally how the university lecture organized. Well, this is actually another thing. There's actually another thing behind it, is that I take my experience as an example. For our high school lectures, our content are fairly light, right? Every lecture, I think the teacher will never go for, I don't know, 5 pages, 6 pages maximum. However, if you go to the university, everything changed. I take my experience as an example. I actually went to there was a one lecture called Introduction to Computing, because I'm actually doing computer science in my everyday life. So in the introduction to computing lecture, the textbook is like 2,000 pages, and we only have like 10 lectures, 2 hours per lecture. So that being said, the teacher has to cover more than 200 pages in one lecture. So that being said, the teachers actually their speed is super fast because there are so many things to cover. And during the process, it is quite possible that a student gets stuck at a certain step. For instance, the teacher say, for now, a plus 2 equals to 2. And then based on a plus 2 equals to 2, we have all the other conclusions. It is quite possible that some student get stuck at, okay, why a plus b equals to 2? But how it works for the university level is that you need to take it, even though you don't understand 100%, but you have to buy it and take it, and then use the conclusion to move forward, to follow the teacher to the other conclusions. And then when the teacher gets started and get to like the gap time, they say, okay, I'm done with this part. Does anyone have any questions? You can raise your hand. Hey, teacher, I don't understand why a plus b equals to 2. That's basically like the rationale behind it, how the university level lecture works. But for you guys, you're kind of in like a relatively lower grade. So Rome wasn't built in a day. It actually took 100 years, right? So let's do this gradually by gradually. So I like to just take this opportunity to give you guys such a training. So try to train yourself such a capability or like a skill, to learn a concept in a very fast space fashion. And then if you have any questions, hold it maybe for 5 minutes or 2 minutes before the teacher asks you. Because I'm going to be here all the time. I'm going to be asking you a question and answer your questions. But gradually by gradually, let's try to use such a practice to, enrich our capability to basically learn new stuffs. All right. So moving forward, section number 4, interaction. Interaction is always important, always and forever. So talking about the interactions, even though you're in the regular day school, you have the face-to-face, like the encounter with our like real professors or real teachers. So it's always important that you need to do the interaction. So there are many ways to interact in our lecture. The most common way is actually you can unmute yourself. Normally, when you enter the lecture, I'm going to put you into mute, so you won't be so many interactions with the other guys. Well, you can actually unmute yourself, and you can basically answer my questions. Or you can ask the questions over the course of the lecture. So it is not a big deal whatsoever. Well, if you do not like to talk, there's another way for you to chat with me, is that there's a control console on your interface. You can see the mute, stop video, manage participants, so on and so forth. In the very end, there's a 3 dots, says more, right? You can click the 3 dots, and there will be a drop-down menu. The first option in the drop-down menu will be chat, right? You can actually open the chat window. So I want you guys, can you just do a quick try? Everyone can have access to this chat window. Can you just type a hi or like whatever to make sure I can see you guys? Okay, that's perfect. Actually, you have 2 ways to chat with me. You can either chat publicly, so everyone can see your answers to your questions, or if you're a little bit shy, you can actually choose a private chat. You see, by default, you're going to see the to everyone. If you click, there's an arrow pointing down. If you click arrow pointing down, you're going to see there's a bunch of names. You can choose my name from the drop-down list. So that being said, you're actually chatting privately with me. If you think, yeah, I see somebody already, give a try. Yeah, just give a try. And that's pretty much. And you know what? There's no bad answers. There's no bad questions. Like the insurance company, right? You see the advertisement. And any problem, you can chat. You can give us a call. There's no bad questions. The same thing applies for our lecture because this is a learning process. There's no bad answers. There's no bad questions. So no one is going to be, judging you by your answer. So no worries. Okay. Number 5, homework. Homework is very important. I take homework as an extension of our lectures. We always give you the concepts, the ideas, and the sample questions. And afterwards, you need to do a real practice. Get your hands dirty. That's the best way to learn new concepts, right? Normally speaking, our lecture is once per week because we're talking about something a little bit difficult. It's more difficult than our regular day lectures, like day schools. But here, for this time, we're actually doing a everyday lecture. So what's going to happen is that every day after the lecture, like today, after this lecture, I'm going to present the homework into our Google Classroom. So you have one day to finish the homework. So you can try your best. So it's not a big deal whatsoever. So in the next lecture, at the very beginning of the next lecture, I'm going to spend some time talking about every single problem in our assignment. Because I believe to make sure every single problem can be properly taken care of, properly explained, this is more than important. Normally, I will ask some students to participate in this process. So this is how it works. If you finish your homework, you can upload it to the Google Classroom. I'm going to be marking your assignment and give you the feedback. If I think your solution is very nice, well organized, I'm going to be introducing you to give us a presentation, a very short presentation for the very beginning of our next lecture. You can share with the other guys how do you think for the problem. Okay, and one more thing, bear in mind. So, like, if I ask you to do the presentation, it means that your homework is fantastic for this part. So I won't be making you like a fool, right? If you did a wrong answer, so I won't really ask you to do the presentation. So I want to make sure, everyone has been introduced and is actually doing a good work for the presentation. Okay, and why I'm doing this? Because I believe, you know, this is actually due to my personal experience. Most of the Asian students, we are actually knowing a lot of things from A to Z, but the presentation skill, especially doing the presentation in front of the public, it's a little bit challenging. So sometimes you know the answer, but you don't really know how to present it properly in front of the public. So that being said, I really would like to take every opportunity with you guys to make sure you can, try to present as much as you could. And also another very important thing is that eventually, if you want to go to, like the job interview or something, it is always important just to speak, what should I say, think a lot, right? Think a lot. I'm actually doing computer science for all my life. So as long as do an interview for different top tier companies, let's say Google or Facebook, when they give you the code interview, these days, they're no longer give you like a laptop or something, you do the coding silently. No, on the contrary, they will give you a whiteboard. You're gonna basically walk through the interviewer as interviewee, right? You're gonna walk through the interviewer how you write a code. So whenever you write a code, you need to present how do you think, what is the advantages, what is the disadvantages, the pros and cons. So people will ask a question, interrupt you in the middle, and you need to be ready to, ready for all the challenges. So that's actually, I think, is very important. Maybe you guys are a little bit young, but it is never too early to, basically, what should I say, help you guys create, if not enrich, this soft skills. Okay, so that's actually why we have this homework section. And then the presentation. So normally speaking, I will ask one student, normally speaking, to do a presentation for each lecture. You can find out a question, not necessarily super complicated question. We can find out just like a question that you think is comfortable, and taking from there, you want to give us a presentation. Again, the most important thing is you want to show us how do you think. Working as a teacher, there was actually saying in English, if you want to be a pro in a topic, just be the teacher of it. whenever you're doing the teacher, you're presenting the ideas, it's actually very important that, it's actually very helpful for you to basically ramp it up and be ready for all the questions. All right, so I think there's a short and brief introduction. Hopefully it's not so long introduction to give you guys an idea, because normally we have some new students for each lecture. I want the students and understand, who we are and where we come from. So far so good? Okay. If any questions for me? No? Okay. If there's no questions, so let's go to the real content of our lecture. So like I said, I'm going to be here and I'm going to be number theory. Yeah, so let's get started. This is number theory, our first topic. Okay, number theory is actually a very old topic, and still it's very important and a very difficult problem, you gotta say, especially for the math competitions. The Canadian and American math competition is pretty much the same. They focus a lot for the number theory, especially the last 5 questions. They always ask you something pretty much focused on the number theory. Actually, number theory is not a new topic. It's actually an old topic. The time when people realize there are numbers, people realize we need to investigate the properties of the numbers. Number theory is nothing but trying to investigate and finding out the patterns, the principle of different numbers. Gauss, a famous mathematician, actually used to say, mathematics is the queen of science, and number theory is the queen of mathematics. Just trying to say how important the number theory is. Actually, later the people actually changed Gauss's word. They say mathematics is the queen of science, and number theory is the crown of the queen. And Chinese people actually add another word afterwards, saying that the Goldbach Conjecture is actually the biggest pearl on the crown. So nothing but trying to say how important number theory is. And during the number theory part, we're gonna see a lot of important names. So these names are very glory, very shiny names, or this very glory mathematicians in the math history. They did a significant contribution to the number theory. I'm just gonna let you know some names, because we're gonna see these names quite a lot during our lecture. First one is Euclid. We should be very familiar with Euclid, because even our water road exam is actually named after this mathematician. We know that Euclid is actually a pioneer for the geometry, right? He created the Euclidean geometry, but also he's an expert in the number theory. He actually found out there are infinitely many prime numbers. People might find it's very intuitive. You have 5, 5, 7, 11, 13. There's so many. But in mathematics, something very intuitive might not be something so easy to be proved, right? Because in mathematics, we're always trying to find out a rigorous proof for all the problems. Euclid actually find out a method trying to prove there are actually infinitely many prime numbers. And actually, his way to prove this concept is actually very useful. We're going to introduce the way that he proves the theory, and then we're going to use it to a lot of following problems. So this is actually a very important trick for the number theory related proof. And also, he actually created the fundamental theorem of algebra. What is the fundamental? The name sounds it's very big, right? The fundamental theorem of algebra. Actually, it says nothing but like this. A positive integers, p, if I like to do a prime factorization, so the prime factorization can be written as k1, k2, all the way to kl. So this is n1, n2, all the way to nl. So this kind of the prime factorization should be unique. I'll give you an example. 36 can be written as 2 to the power of 2 times 3 to the power of 2, right? So this is a prime factorization. Bear in mind, we're talking about the prime factorization, not any factorization. The prime factorization. The prime factorization for 36 is 2 square times 3 square. And Euclid actually proved that. this kind of factorization is actually unique. You can always find only 2 2's and only 2 3's. It is impossible you find another factorization also for 36. Okay, that's actually the basic of all the algebra. So we call it the fundamental theory of algebra. That's for Euclid. We're going to see the names from time to time. The other person is Fermat, or like Fermat. Fermat is also a very famous French mathematician, and he actually contributed a lot of parts in the entire mathematics. Well, for the number theory part, 2 things we need to remember. The first one we call the Fermat's little principle. So this principle will be covered in our lecture. It actually gives you the relationship between the prime numbers and corresponding modular arithmetic. The other important part is actually another very interesting part is the Fermat's last principle. This is actually a very famous conjecture by the time then. You know, what happened is by the time then, the mathematician, by the way, this is actually from 300 BC, right? Before the centuries. Fermat is from like 17th centuries. By the time then, like the mathematicians, you know, they can't send emails. So by the time then, they can only write letters. So basically, when Fermat write letters to all his mathematician friends, he always says something like this: "Hey, look, I find out a new principle. I prove it already. However, due to the limited space, I don't have so many space in the letter, so I just ignore the proof. But I got it already." You know, something like this. So he keeps saying that again and again. So whenever we create a new conjecture, people trying to find out the proof. But only one thing, the Fermat's last principle, he claimed once again. He has no space, but he got a proof already. But people get stuck. People have no idea how to prove the famous last principle. All the way until 1995, almost after like 300 years, people got a proof. It's actually proved by a British mathematician, Andrew Wiles. This is almost after 300 years. So Andrew Wiles actually, you know, did a lot of job to figure out how to prove the Fermat's last principle. So after he published all his proof, actually, like a journalist did an invitation, I did an interview, and like the journalist asked Andrew, so what do you think? Is it possible that Fermat actually proved it already? And we wait for like 300 years to actually get it proved. So what do you think? After 300 years, you proved something that Fermat claimed he already proved 300 years ago. So Andrew's answer is pretty direct. He said, you know what? This is a 20th century problem, a 20th century proof. No one can prove it before the 20th centuries. So this is kind of like a trick that people are trying, especially for the, you know, for the 19th century, for the 17th centuries or like the 18th centuries. A lot of mathematicians, they prove something or they claim to prove something, but they never show the evidence. And by the time then the mathematician is kind of like a competition. Who can create something, who can prove something, he will be considered a pioneer of this field. So it's kind of like something interesting. So Fermat is pretty much doing this. So in Chinese, we're pretty much like he's like a 挖坑专业户, like 郭德纲, always raise a problem, but never really give the official solution for the problem, so on and so forth. And then the other one I want to say is actually Euler. Euler is actually another very famous name we need to remember for the number theory. So Euler is pretty much like a god. It's pretty much like a time traveler. He's like so smart. I'll give you some information regarding his biographs that you can remember, and then you can realize how strong or how super he is. He graduated and got a PhD. He graduated and got a master degree when he was 15 years old. And when he's 19 years old, he graduated with a PhD degree. When he was 20 years old, he becomes the principal of the Russian Academy of Science. You know, by the time the European countries are more connected than nowadays, you don't have to be a Russian to become the principal of the Russian Academy of Science. But he was only 20 years old. And he actually created a lot of mathematics denotations, and most of them are very important for our use for these days. For instance, fx is created by Euler. And all the trigonometry-related denotations, sine, cosine, tangent, all of them are created by Euler. So without Euler, we don't even know what they are. So he created all these denotations. And you know what? 50% of Euler's work was created when he was handicapped. So his right eyes become blind when he was 28 years old. So pretty much 50% of his work is done when he was like one eye blind. Well, the other 50% was actually done when he was completely blind. He was completely blind at 59. So like Beethoven, right? You are a superstar. You don't even have to listen. Beethoven is completely deaf, and then he can create music. The same thing for Euler, totally blind, and also create also so many theorems. And at the year of 76, when he was in the lab, all of a sudden he stand up to say, he said, I'm gonna die. And then he fell over on the ground and died right away. So his life is pretty much like a urban legend. You have no idea, right? It's like he can predict. It's pretty much like a prophet. He can predict a lot of things happen in the future. So Euler's contribution, actually two things. One thing, he actually proved the proof of Fermat's little principle. See, the Fermat has like two principles. The first one is actually proved by Euler. The second one is actually proved after 200, 300 years. This is actually the first important contribution of Euler. The second important contribution is the Belfontaine equation. Right? We talked about the Belfontaine equation previously. Belfontaine equation means, let's say, x plus y equals to 3. Just give an example. 3x minus y equals to 4. You have two equations and you have two variables. Normally speaking, you should be able to find a solution, right? However, if you have two variables, but you have, give this, you have only two equations, but you have three variables. Of course, everyone knows that you're going to have infinitely many pairs of solutions for this problem, right? So it's kind of like meaningless for us to find out what is all the solutions. So these kind of solutions, we call it a Belfontaine equation. Belfontaine is a king's name. He's a king plus a part-time mathematician. So we actually did a lot of research on how to find out the solutions for the Belfontaine equation. Especially if focus on the integer solutions of Belfontaine equation. Because like I said, there are infinite many pairs of solutions for Belfontaine equation. It's kind of meaningless to do any investigation. Well, if we put a little bit constraint, we're only talking about the integer solutions of a Belfontaine equation. So this makes us more reasonable, makes more sense for us to do the further investigation. So Euler actually, along with the Belfontaine, they did some fundamental contributions for the Belfontaine equation theory and related problems. And the last but not least is Goldbach, right? The famous Goldbach conjecture. Even for today, we don't really got a pure proof, a very pure, rigorous proof for Goldbach's solution, for Goldbach's conjecture. So that's the reason we still call it a conjecture. People use computer trying to find out so many numbers. I think they find out 10 to the power of 48. All those numbers, they're all meet the Goldbach conjecture, but this is mathematics. People need to find out a rigorous solution, right? A rigorous proof. And this part, like our Chinese mathematician Chen Jingrun, who did a very good job, and he was pretty much like the pioneer for the entire world, finding out the proof for the, for the Goldbach conjecture. All right, so this is kind of like some like gossip, some basic information, like kind of the names you're gonna find out for the number theories. But for our lecture, of course, we won't go for that much deep. We're gonna focus on something more related to our related knowledge. We're gonna focus more on something like divisibilities, the prime numbers and composite numbers. The greatest common divisor, least common multiple, like the modular, like the modular arithmetic, and some very important principles in our high school related math competition. So the following lectures, we're gonna pretty much one lecture or two lectures for one topic. We're gonna go deeper in all those knowledges. Okay, so let's go to our first lecture. We're gonna focus on the divisibility part. Divisibility is actually a very, I think should be a very familiar concept. You guys learned divisibility pretty much from your elementary school. So let's go for some basic recap of different definitions, different principles, pretty much help you guys to review before we go to any questions. Okay? So what is the divisibility? Here comes the definition. An integer b is divisible by another integer a. Of course, a cannot be 0. So we can write as a pipe b. This is nothing but a denotation. We use a pipe to say b can be divisible by a. Or we can say a is a divisor of b. Nothing more but a pipe. But nothing more but a denotation. Pipe is just like the vertical line, okay? If there is an integer x such that b equals to ax, we call b is a multiple of a, and a is a divisor of b, right? This is like the basic concept, like a basic concept. So if you have any problem, let me know. I'm going to send you to the elementary school and you can relearn it from scratch. But basically, we can say 2 is a divisor of 4, right? 10 is a divisor of 100, right? It's pretty much a denotation we're going to do. So that being said, we're going to talk something about a proposition. Propositions. Based on the concept, on the definition, we're going to find out some propositions. And most of the propositions are fairly intuitive. You can understand it right away. The first one we said, if A is a divisor of B, then A is a divisor of minus B, right? And vice versa. If A is a divisor of B, then minus A should be also a divisor of B, and vice versa, right? So that being said, actually, this kind of sign doesn't really change our analysis too much, right? A positive number, like a negative number is pretty much the same thing. So therefore, most of the time, without really a specific indication, we're pretty much saying that all our investigations focus on the positive integers. Okay, unless specified explicitly, we're pretty much focused on the positive integers. Number 2. If A is a divisor of B, B is a divisor of C. So therefore, A will be a divisor of C, right? So it means that this divisibility can actually be passed on. A is the divisor of B, B is the divisor of C, C is the divisor of D, whatever, you can actually pass on this divisibility property. I think it's also very understandable. 1.3. A is a divisor of B. A is a divisor of C. Then A must be a divisor of Bx plus Cy for all integers x and y. Does it make sense? Two numbers, A is the divisor of B, A is the divisor of C, then any kind of like bx plus cy combinations will be also a multiple of A, right? Okay, this part I want to give you a quick note. This kind of like a linear, right? I do it because they're actually in the order of one. A linear, and then add them together, subtract them together. Whenever you go to the college to learn the linear algebra, actually this expression has a name. We call it the linear combination. The linear, because you see, they're all like the exponent is always like the first order, right? So this is a linear combination. So that being said, if A is a divisor of B, A is a divisor of C, so A must be a divisor for all the linear combinations between B and C, right? You can actually put it to multiple numbers, B, C, D, F, like whatever. As long as it's a linear combination, it's always good. Next one. If A is a divisor of B, B is a divisor of A. So therefore, A must be positive or negative B, right? If you have like two numbers, they are a divisor for each other, so they can only be the same or only assigned apart, right? Which is also quite understandable. Like I said, most of these concepts are pretty much very understandable. You guys should got it like in your elementary school. 2.5, we call it the quotient theorem. Even though the theorem is also a very understandable concept. Given AB belongs to integer, B is not equal to 0, then there exists only a pair of integers, Q and R, such that A will be equal to B times Q plus R. R should be from 0 to B absolute value. It means that if you want to do a division, you're gonna have a quotient and you're gonna have a remainder, right? And this kind of quotient and remainder must be unique. There exists only one pair of. For instance, 5 divided by 3, you're only gonna have 1 as a quotient and the remainder as 2. There's no way around. There must be only 1 and 2. Now, most of this very intuitive theorem for mathematics, it's very intuitive these days, but back to like 2,000 years ago, people actually spent a lot of efforts figuring out why it is, okay? So especially I want to say the Q would be called is a quotient, right? And the R will be called is a remainder. These are like a basic concept for everything. 2.6. Some useful conclusions. First one. Given n, A belong to integer, n must be the divisor of A plus 1, A plus 2, A plus n. This is like a mathematics language, right? So who can tell me what is the human language for this expression? We always have like two languages, the mathematics language and human language, right? The mathematics language says something like this. What is the human language for this expression? Okay, so let's pause the video from here for a sec. Who can tell me what is the human language for this? n is the divisor of a plus 1, a plus 2, all the way to a plus n. This is more like mathematical language, right? What is the human language? If you want to translate into human language, what does it mean? Who can tell me? Hey, guys? You wake up? Guys? Who can tell me what's the human language between this? N can be divisible by n consecutive numbers, the product, right? The product of n consecutive numbers. Is that right? N should be a divisor of n consecutive numbers, their product, right? And also that being said means what? For every n consecutive numbers, there will be one number which is a multiple of n. Is that right? For every n consecutive numbers, there will be one number, at least one number, who is a multiple of n. Right? This is like the human language, how you translate it. Is it good? Okay, so let's continue. So we need to know like how to translate between the human language and also
It actually
the mathematics
means
language.
n can be a divisor of the product of n consecutive numbers.
Is that right?
These are n consecutive numbers. The product of n consecutive numbers must be a multiple of n. Give an example. 3 must be a divisor of 3 consecutive numbers, whatever, 19, 20, 21. 4 must be 16, 17, 18, 19. Okay? So this is what this theory says. So the proof of the theory should be it's actually fairly intuitive. You see, as you can see, for 3, let's start from 2. For 2, every 2 numbers, you must have a multiple of 2, right? Odd number, even number, of course the even number will be a multiple of 2. For 3, every 3 numbers, you'll be able to find a multiple of 3, right? Every 3 numbers, you'll be able to find a multiple of 3, regardless where you want to get started. And the same thing, 4, every 4 numbers, you'll be able to find a multiple of 4. 13, 14, 15, 16. I got 16. So all the way, whenever you got n numbers, every n numbers, you will be able to find a multiple of n. So that being said, there must be one of them as a multiple of n. But you don't know which one is them. You don't have to, right? As long as you have n consecutive numbers, you do a multiplication, there must be a multiple of n. Okay, you guys follow me in this part? All good?
So far, so good? Right? I think the proof is very intuitive. Okay, all good? Okay, so let's continue. Yeah, if you have any questions, please let me know. Like I said, if you feel a little bit shy, you can privately chat with me. As long as you see the chat, I'll answer your questions. All good? Okay. The second part, exactly the same. Given n, a belong to integer. For now, I want to say that n factorial must be also a divisor of n of the product of n consecutive numbers. So the previous one we say n is a divisor. Now I say, okay, not only n factorial is also a divisor of the product of n consecutive numbers. You can just list out some numbers, you'll find out this is always true. Okay? Third one. Just a quick comment. Do you guys know how to prove the second one? Anyone want to say something? How to prove the second one? N factorial, you know how n factorial works, right? N factorial is actually 1 times 2 times 3 all the way to n, right? N factorial must be a divisor of the product of any n consecutive numbers. Actually, it's quite understandable as well. You know what? for each consecutive, like n consecutive numbers, regardless where it gets started, right? It's gonna have a remainder for n, right? Let's say a plus 1, you use this number, divide by n, the remainder can be 1, for instance. And then a plus 2 will be 2, right? A plus 3 will be 3. All the way n plus n will be n. You time them together, it will be exactly n factorial. And same thing applies if you get started with not from 1, you start from 2, for instance. So a plus 1 divided by n will the remainder 2. And then the next term will be 3. The next term will be 4. All the way, you go to a plus n minus 1. The factorial, okay? If you do the remainder, it will be n, right? So the next one, this is more like a cycle. You go to 1, 2, 3, 4, 5, n, and then jump to 1, 2, 3, 4, 5, n, and jump to 1, 2, 3, 4, 5, n. Okay? I think this is also very intuitive. If you want a proof, you can actually use this verbal proof. Okay? So far, so good? So I need some feedback, please, okay? So like no one is talking to me. I just want to make sure you guys are still like with me. Is it good? So far, so good?
Yeah.
Okay, perfect. Thank you. So let's continue, okay?
a plus b to the power of n. If you use this guy to divide by a, the remainder will be always equal to b. A plus b to the power of n. If I use this guy to divide by a, the remainder will be always b. Who can tell me how to prove this? Who can tell me how to prove this? This is actually something also very quick. It is not going to be a huge, huge proof. Any ideas? Of course, a, b, n, they're all positive integers for sure, right? Positive integers. How to prove this guy? So it's also a very intuitive proof. Any ideas? Not necessarily induction. Induction is too much. We just want to someday I got some students private chat me induction. Yeah, induction I think is good for sure. Induction can be something pretty powerful to get it right. But you have a very quick proof. Just do observation. You know what? Just do a quick observation. This guy, you can actually use the Binomial Theorem to expand, right? The Binomial Theorem to expand. You're going to find every single term, you're going to have an A, except the last one. The last one, you're going to have a B there. And then you just basically do a division, you'll be able to find out how it works, right? Do you guys know the Binomial Theorem? C and I, AI, B and minus I, right? I from 0 to n. Using a binomial expansion, you'll be able to prove it fairly quick. This is not something so tricky. Yeah, of course we can do induction, but induction is going to be too lengthy. You basically do this, you can find most of the terms they have A, only one term doesn't have A, that term you divide it by A, of course, the remainder will be B. Is it good? Okay, the last one. The last one is actually very important. AMC and also the Canadian exam test the last principle from time to time. That is the name of number of factors principle. What is that? Something like this. Given n is a positive integer, n can be written as the factorization form. Okay, we do a prime factorization. Maybe we're going to say a prime factorization form. Yeah. Any numbers can do a prime factorization, right? N will be written as P1, K1, P2, K2, PL, KL. So here I want to say P1, P2 all the way to PL, they're all prime numbers. Okay, if I give you a number, the number of course can be can be done for a prime factorization. I'm just going to list out all the prime factorizations, something like this. Okay, then nth factors, big N, can be written as big N equals to K1 plus 1, K2 plus 1, all the way KL plus 1. If you have a number, I did a prime factorization. So by using the prime factorization, I will be able to determine all the factors of n. All the factors of n here, of course, it includes 1 and n itself, right? All the factors, I put them together. The total number of all the factors will be K1 plus 1, K2 plus 1, all the way to Kn plus 1, right? To prove this is also very intuitive. You see, this part equals to here. So that being said means I'm trying to do a multiplication principle, right? Counting probability, multiplication principle. For the first factor, I can choose P1 once, twice, 3 times, all the way to K1 times. And also I got an option, do not choose any K1, right? So that being said, you have K1 plus 1. You guys follow me? You can choose P1 once, twice, all the way to K1s, because it only has K1s. You can't take more than K1s. But you also got an option, you don't choose anything. Leave 1 as there. So you have K1 plus 1 for the first option, talking about the P1.
Hey there, I think somebody have a question, right? What is the K and what is P in this case? P and K, okay, let's get started with P. P is actually the prime factors. If you have a number, you can actually do a prime factorization, right? You can actually break them into all those prime numbers. So P1, P2, all the way to PL, they are the prime numbers. And K1, K2, all the way to KL, they are actually the exponents of those prime factors. So, for a number, I can actually write it into a prime factorization. So that being said, for each prime factors, they can have different exponents. So K and P stands for this. Okay, just try to answer somebody's question. And then as a multiplication principle, you can keep doing that for P2, P3, all the way to PL. So that's the reason the total factors for n will be pretty much K1 plus 1 all the way to KL plus 1. I'll give you an example to make it more clear. Yeah,
36.
I think the example will be better.
36 can be written as 2 to the power of 2, 3 to the power of 2, right? So if you ask me what is the total factors of 36, it's going to be 2 plus 1, 2 plus 1.
The exponents.
Just these two numbers, and add them together using plus 1. That's going to be 9. The total factors of 36 will be 9. Let's list them out. It's 1, 2, 3, 4, 6, 9, 12, 18, 36. These are the total numbers for 36. You can do the same things to verify more numbers. Okay? So these are pretty much a basic knowledge for all the divisibility related concepts. Like I said, it's fairly intuitive. This is not a rocket science, so you can understand it fairly quick. All good? If all good, let's go for some questions. You'll see how we can use these principles to solve all our problems. All good?
So any questions so far? All good? Okay, if all good, let's continue.
Okay,
there's nothing really
move
special,
on?
right?
Is it good? Okay, let's go to our first question. Question number 1 is a warm-up question. A warm-up question. given a, b, n belongs to the positive integer, for any given k belongs to the positive number. Okay, for the new students, you might know this. This actually means, this is nothing but a denotation. It means for any given. Just try to make like the 3 words into a simple sign, for any given. So this is actually come from the word arbitrary. And then they just upside down the A from A to here. Okay? So actually, I keep using 2 denotations you guys need to be familiar. One is this guy means for any given. Another one, this guy, E. I use E, but I just not upside down because upside down E is the same thing. The upside down is the same thing. So I do the flip to the right, a flip to the left. So that one means there exist. There exist. It's nothing but a denotation. Just try to make our language shorter. Okay? Please prove, not please prove, here, for any given k belongs to the positive integer, you have b minus k is a divisor of a minus k to the power of n. I'm just going to erase this part. Okay. So, please prove. b minus k is also a divisor of a minus b to the power of n. Okay, that's the question. You have a, b, c, 3 numbers, positive integer. The question gives you b minus k is the divisor of a minus k to the power of n. And what you need to prove is that b minus k is also a divisor of a minus b to the power of n. Okay, this is like the first question. Let's do this together. Okay, I'll show you guys how to do the analysis and how we're gonna decompose the problem and find out a solution. For our old students, our old mates, we should be familiar. I keep asking you a question. For any problems, before you jump to the real solution of a problem, the first step is trying to do some observation, right? Where all our investigations should be based on the observation. So the first step, like the $1 million question is always, how can you do the observation? And what you can find out based on the observation. Let's have a quick observation for the problem. The problem is trying to prove something as a divisor of another thing. Basically, they give you something as a divisor of one thing, and they want you to prove something as a divisor of another thing. A quick observation says, this part is the same. B minus k is a divisor of something, and you need to prove b minus k is a divisor of another thing. Okay? So the second step, we need to do observation for the right-hand part, the part on the right-hand side of the pipe sign. A minus k to the power of n, a minus b to the power of n. So for sure, we're trying to find out some relationships between this a minus k to the power of n and a minus b to the power of n. And taking from there, we might be able to do some investigation and figure out where we come from. Obviously, a minus b to the power of n can be written as what? A minus k to the power of n, this is exactly what I have, and minus b to the power of n, k to the power of n. Right? You just do a quick comparison between these 2 forms. These 2 guys, you'll be able to figure out, right? This is what I have. What I know is that this part is a divisor of b minus k. Right? This is actually given by the question. This part is what I need to prove. So it looks like the $1 million question comes to here. This part, is it going to be a multiple of b minus k? This part, is it going to be a multiple of b minus k? b minus k is a divisor or not for b to the power of n minus k to the power of n. Right? It's very intuitive, right? Because you're going to ask you the same question whenever you're in the exam. I know this part. I need to prove this part. Of course, I'm going to analysis for this part. There's nothing more I can do. So b minus k, is it a divisor of b to the power of n minus k to the power of n? This part is actually a very important factorization that everyone needs to remember.
Let's pause it from here. Does anyone know this? B minus k, if I want to prove this guy is a divisor of b to the power of n minus k to the power of n, apparently I'm going to do some factorization, right? So who can tell me, who knows the factorization? B to the power of n minus k to the power of n. Who knows it? No? Okay, maybe you don't learn this in your day school, but this is actually something very important. In any kind of Waterloo math competition, they will test you. This is a very commonly used expression that you need to know. Okay, please focus in the following part.
This is a very important factorization that everyone needs to remember. B to the power of n minus k to the power of n. Who knows? How can I do the factorization for this guy? Who knows the factorization for this guy?
This is important part.
This is a very famous factorization. It can be considered as a proposition of the binomial theorem. Binomial theorem can be long, but this guy can be pretty brief, and you guys need to remember. B minus k minus b to the power of n minus k to the power of n. Or something more brief, a to the power of n minus b to the power of n, something like this. This is actually something very important you need to remember. The factorization goes like this. B minus k, bn minus 1, bn minus 2k, bn minus 3, k squared, all the way b k n minus 2, k n minus 1. So this is the famous factorization for such a form.
You need
Try to remember this.
Important.
Because we keep using that from time to time. Okay? So you guys familiar with the binomial theorem, you're going to say this is exactly the binomial theorem. But we're not going to go for the binomial theorem too much for the current lecture. We're just going to ask you guys to remember this factorization. And also, something like x to the power of 4 minus 1, xn to the power of 4 minus 1. They're exactly the same using this form. This is going to be x minus 1, xn plus 1, because 1 is already done, right? n plus 2, n plus 1. Oh, excuse me, n minus 1. N minus 2, x plus 1. Something like this is very important. Please bear in mind. Okay? So these are the very important factorizations for pretty much you guys need to know in the future. Okay, if we're all on the same page, for sure this guy will be a divisor of b minus k, right? Because it already has a b minus k up front. Okay, then that's great. Therefore, let me just rewrite it, okay? We're trying to say ba minus b to the power of n equals what? A this minus. Okay, I have already know this is given by the question. B minus k is a divisor of a minus k to the power of n. This part, I have already know this is actually based on my proof. B minus k is also a divisor of this, right? So, if b minus k is a divisor of the first term, b minus k is a divisor of the second term, then for sure, b minus k will be a divisor of the sum or difference between the two terms. Is that it? Still remember, this is a very important theorem we just introduced. If A is a divisor of B, A is a divisor of C, then A must be a divisor of bx plus cy. Any kind of linear combination, you'll be able to find out this is a multiple of A. You guys follow me? Is it good? Yeah, this is like a warm-up question. This is not something too difficult. But what I'm trying to say is, most of the important thing is that you need to do a little bit observation. Do not directly go to the induction or expand them. That's too much. We can do that later. But before we jump to the real calculation, real analysis, we need to think about it. What do we have? To do a quick observation, because the observation says the left-hand side are exactly the same. There's nothing we can do. The right-hand side, of course, we're going to try to do some investigation to find out the relationships between what I have and what I'm trying to prove. You always have pretty much like two things, what you have and what you're trying to prove. You always make up the relationship between what you have and what you need to prove. This relationships sometimes takes a little bit longer time for you to build up, but as long as you find out the relationship, all the problem can be solved right away. And also one more thing I told you guys, please try to remember this. This is an important factorization you need to remember. In today's lecture, in today's assignment, question number 1, you're exactly using this. Because our assignment, the questions in our assignments, it's actually designed to make sure it go with the sample questions we introduced during the lecture. So understand the lecture and do the assignment, it will be considered as a reinforcement. So the same technology will be used for the assignment. So far, so good for question number 1. It's a warm-up question, okay? Any questions, just let me know, okay? Any questions for question number 1? Oh, good? Okay, oh, good. So let's continue. Like I said, it's very dynamic lecture, so you can always interrupt me. If you think I'm bullshitting, you can always stop me. Okay, no problem. So let's go to question number 2. Question number 2 will be a little bit more difficult. It's 1989 Amy question. Okay, if you see Amy question, you might think it's too difficult, but don't forget it's 1989. The 1989 Amy question for now is pretty much like a Waterloo level question, because the complexity of all the math competition is getting increased exponentially. So at the end of the day, it's pretty much more and more difficult for all the exams. Do you guys still remember, for the old students, we used to give you guys a 1975 IMO question. 1975 IMO question. These days, I think it's nothing more but a Euclid question, because the complexity is ramping up like crazy. Okay? This question says like this. If you have 5 numbers, A, B, C, D, E. A is less than B, less than C, less than D, less than E. Are consecutive positive integers such that B plus C plus D is a perfect square. A plus B plus C plus D. Okay. We have 5 numbers, and they're consecutive. There are consecutive numbers, A, B, C, D, E. Well, 3 numbers, B plus C plus D, will generate a perfect square. 5 numbers, adding them together, will yield a perfect cube. It's very understandable, right? So here's the question. What is the smallest possible value of C? What is the smallest possible value of C? So it looks like you can find infinitively many such group of numbers, 3 numbers can be a perfect square. 5 numbers sum can be a perfect cube. You can find so many, but of course the question only asks you the smallest or like the biggest, so on and so forth. So a student asked, are the Amy questions inspired by the math contest from another country? Yeah, of course. So those authors, they're not prophet. They can't create too much questions by their own. They basically read the questions from the other countries, and then taking from there, they basically get their database, trying to figure out a question. The math competition, do you still remember this math competition? The high school math competition thing was actually created by Romanian. So before Romanian, there's no high school math competition. Romanian is the first country in the world who create, I think in 1970 or something, they create like the first level of this Romanian Math Olympia for high school students. And afterwards, Russian and all like the Eastern European countries actually just catch up. They have like the math competition, and Canada also, in the United States, we also just basically participate in those. So to answer your question, we're not like superheroes. We always create, but we cannot create a question from scratch. They basically check the other questions. Sometimes they just do a very minor change. I do remember there was like a Canadian question. Canadian MO question, like CMO question. It's exactly the same as one of the, I can't remember, it's Vietnam or something, like pretty much long time, 10 years ago. They just copy paste without changing too much. So that's to answer your questions. But the good part is different math competition, they're always, the concepts are similar. Of course, like the complexity can be different, but the concepts can be similar. You learn one thing, you'll be transferred to the other stuff. Okay. Have a look for the question. You have 5 consecutive positive numbers. 3 sum, like 3 number sum is a perfect square. 4 number sum is a perfect cube. And yeah, so we're trying to see how we can find out the number. Okay, before we jump to the solution, I'd like to give you guys some common sense. Okay, common sense is always important. Okay, first thing first. Whenever you see something like this, 5 numbers in a row, they are consecutive numbers. 5 consecutive numbers, who can tell me your first reaction? What do you need to react for 5 consecutive numbers? What kind of special properties for this 5 consecutive number? Maybe 5, 6, 7, well, whatever. Consecutive numbers means what? The question number 1, who can answer me?
So let me ask you guys. So consecutive numbers means what? Your first reaction, as long as you see the consecutive numbers, what should be your first reaction? Let me see, some students already have the answer. Yeah, I see somebody already have the answer. You know what? The consecutive numbers actually means they're just like apart by 1, right? Can be a plus 1, a plus 2, a plus 3, a plus whatever. So they actually form a what? An arithmetic sequence, right? Have you guys know the arithmetic sequence? Can you give me some response? Do you guys know arithmetic sequence? Yeah, like arithmetic sequence, right? Means just like the difference between any adjacent 2 terms, they're actually 1. They're actually like a common number, right? A common, we call it common difference. So 5 consecutive numbers automatically means what? They're all arithmetic sequence, right? With the common differences equal to 1. Okay, that's good. Let's continue.
Consecutive numbers means what?
Yeah, from my previous lecture, people are
I see Andy has something. Andy, why don't you give us some ideas? So yeah, I see Ken Yi and Ethan. They both have something similar. Yes, consecutive numbers, the first reaction, there must be just like a arithmetic sequence. Is that right? It's an arithmetic sequence. The common difference is 1. Is that right? That's your first reaction. Because consecutive numbers that doesn't have something too fancy. It's pretty much an arithmetic sequence. Arithmetic sequence, okay. And the question talking about the sum, 3-number sum, 5-number sum. So your first reaction, B plus C plus D will be equals to 3C. A plus B plus C plus D plus E equals to 5C. All right? Arithmetic sequence, that's pretty much the only property you can get from arithmetic sequence. That's exactly what Andy mentioned in the group chat. Okay. The question asks us to do what? What is the smallest possible value of C? Okay, perfect. We're actually denoting these numbers using C. It's exactly what the question wants us to do. We need to go from the, we need to understand where we come from, right? We're trying to find out a C. Okay, that's for trick number 1. Consecutive numbers always means arithmetic sequence, nothing. Trick number 2. Whenever you see blah, blah, blah is a perfect square, blah, blah, blah is a perfect cube, or perfect n to the power 4, n to the power like a quart, like whatever, right? Your first reaction should be, if you say this is a perfect square, okay, I'm just going to let it equals to m squared. I don't even know what m is, but it doesn't matter. I'm just going to put it as m. If this is a perfect cube, I'm going to put it as a m cube. Right? If this is a perfect something, I'm just going to put it there. That's it. Trick number 2. Trick number 2. Just put it there. Okay. Then we have all of this. Let me just write it down from 3C equals to m squared. 5C equals to n cubed. Let's do some quick analysis in this part. I think all the information we got from the question, that's it. Arithmetic sequence, perfect square, perfect cube. Now we need to do a little bit analysis for this. 3C equals to m squared. Because we guys need to be familiar, or at least get familiar with the way that a number theory related problem, how we're going to do the analysis. Number theory related problem, we always do analysis from the factors perspective. You're always trying to do factorization, or always trying to find a factor, or always trying to find a divisibility, so on and so forth. So this is the big direction where we do for all the number theory related problems. This is only the second question. You might not be so familiar, but it doesn't matter. Follow me, okay? Follow me. Let's do several questions. After you did maybe 10 questions, 15 questions, you will get a hang of it. So taking from there, you will know how to take this technology and do the other problems. So that's the reason why we like to consolidate all the number theory related sections together. Because you keep using the same technology again, then you will get a hang of it. If you use it one time, then after 3 months, use it another time, you just basically forget them all. Follow me. Like I said, we always do some factor, some divisibility related analysis. So how we can get started with this? 3C is equals to m squared. So that actually means 3 is a divisor of m squared. Is that right? 3C equals to m squared. Of course, 3 is a divisor of m squared. That is not a rocket science. Let me just erase it first. Well, the next step is the $1 million step. If 3 is a divisor of m squared, so 3 must be a divisor of m. Is that right? Because 3 is a prime number. You cannot chop prime number anymore. If m squared has a divisor of 3, you cannot split 3 anymore, right? If m squared has 3 as a divisor, means both of these two m's, each of them must have a divisor of 3. Guys follow me in this part? This is something very important. 3 is a prime number. You can no longer chop like prime number into any smaller parts, right? So if 3 is a divisor of m square, means m itself must have like m must have a multiple, must have a divisor of 3. So 3 must be a divisor of m, right? If 3 is a divisor of n, okay, I can just let m equals to 3k, right? M equals to 3k. Whenever I have this, always put it back. Always put it back. Because previously I have no idea what m is. Now I know, okay, m must be multiple of 3. Just put it back. 3c equals to what? 9k squared. So that being said, c equals to 3k squared. Is that right? Okay. Same thing. Same technology. We do the second part. 5c equals to n cubed. Of course, 5 will be the divisor of n cubed. Like I said, 5 is a prime number. So there's no way to chop prime. So therefore, 5 must be divisor of n. It only works for prime number, like I said. It doesn't work for composite numbers. I'll give you an example. 12 is a divisor of 6 squared, right? But you can never say 12 is a divisor of 6. It doesn't work for the composite numbers, but it works for the prime numbers. Because if I say 5 is a divisor of 25, then 5 must be divisor of 5. You guys follow me? This is very important, okay? So I write it down, I'm gonna put it here. So
Thomas, okay, I want to have another explanation. So based on this, I think you guys already come up to a conclusion. If a prime number is a divisor of n whatever, n to the power of k, okay, then this same prime number must be a divisor of n itself. Is that right? A prime number is a divisor of n to the power of k. It means that the prime number itself must be a divisor of n. This is very important, and it is only working for the prime numbers. It doesn't work for the composite numbers. An example I just gave you in our lecture. Okay, try to remember this.
Same thing, huh? Same technology. I let n equals to 5k or 5l, for instance. I use a different denotation. I put it back. I'm going to have 5c equals to 125 l cubed. So that being said, c equals 25 l cubed. Is that right? Okay, don't forget where we come from. We're not here to divide what is k, what is l. My question asked me to decide what is c, right? So just forget about like the k and l. There's only like a parameter as a system. But our ultimate goal is to determine c. So that being said, we change different color. We need to find a smallest c such that c can be written as 3k squared and also can be written as 25l cubed. Right? You just find out a c, the minimum c, which can be written as either 3k squared or 25l cubed. From here, there's no very standard method. You're pretty much gonna do some guesstimation. You find out some number, play with it, and figure out what it is. Okay, who can tell me what is the minimum number for c? Who can tell me?
Yeah, I see Jimmy has the right answer. 675.
Maybe, yeah, I see Andy has the right answer. So maybe let us ask Andy to give us some ideas. How do you think? Andy?
Maybe we're going to ask for Jimmy. Jimmy, you want to give us some elaboration how you come to 675? Hey, Jimmy, I see you're unmute yourself. It's up to you. I mean, if your microphone's okay, you can talk. No? It's okay. No worries. Yeah, it's okay. No worries. Yeah, you know what? As long as you feel comfortable, it's not a big deal. Yeah, but you have the right answer. That's it. Yeah.
Are you there?
Yeah, I think like the same thing. They have the
Hello?
same issue as well. So let me try to faster. Trying to give us the answer. But anyway, let me try to zoom it.
L cube.
Yeah.
This is actually 3 times k squared.
You can actually do a
Do some quick
factorization.
analysis. Maybe you just let L equals to 3. That's it. Let L equals to 3. You're going to have maybe k equals to 5 times 3. Right? You'll be able to have a 3 cube, 5 square on the left-hand side. And also 3 cube, 5 square on the right-hand side. Just like a quick analysis, you'll be able to get your answer. So the right answer for C is 675. That's the right answer for the problem. 675. And also, just like a side work, like a side talk, the Amy, all the questions, all the answers for the Amy must be an integer from 0 to 999. Right? So you guys know that? So, you know, what is called AMC is like a multiple choice, A, B, C, D, E. You choose from A, B, C, D, that's it. But Amy is not 100% multiple choice. It's actually every single question you need to give a number. But the number can't be whatever number. It must be an integer number from 0 to 999. So therefore, in the answer sheet, you can also use the computer answer sheet to put your number there. So I think Amy, that's a very good innovation. It actually, so Amy is kind of like, it's not like a multiple choice because you need to give the number. But still, the number is always from 0 to 99, so you'll be able to put it into the computer sheet to let the computer read it for you. Rather than our Euclid, you have to write a huge page, and then people is going to take forever to mark it. Something like that. So it's very good innovation by like the American Math Association. All good for the question? Okay, the question, just quick recap. 2 things need to remember. First thing first, consecutive numbers always means arithmetic sequence. Arithmetic sequence, put you add them together, you know, they're always like the one in the middle, right? 3C, 5C, that is one thing you need to know. Second thing is, whenever the question says blah, blah, blah is a perfect square, just make it as a perfect square. Blah, blah, blah is a perfect cube. Make it as a perfect cube. And then do some analysis based on that. The analysis for the entire number theory should be focused on the factorization, divisibility, so on and so forth. We'll take more questions to get you guys there to figure out what we're going to do for those questions. All good for the current question? Let's go for another question. I'm going to write you the question, and then we're going to go for a break. Okay. This is a 2003 Chinese Western region Math Olympia question. China is big, so they always have like 2 regions. The Western region, like the Eastern region, they have their own math like the Math Olympia, and finally they're gonna get together to Beijing to have like the final, like the CMO, something like that. So the question goes like, this is an interesting question. This is kind of like an easy question for this Math Olympia. Given positive integer. You have positive integers from 1 to 8. Place these numbers on the 8. 8 vertices of a cube. So here's the question. You have 8 positive integers from 1 to 8. You need to place them. You have a cube. You need to place them on the 8 vertices of a cube. So the cube goes like this, right? Okay, you need to place these 8 numbers into the 8 vertices of the cube. But you can't do that too randomly. There's a pattern. You need to make sure that the sum of any given 3 numbers on the same face must be greater or equal to 10. Right? You can't put like 2 small numbers together. Okay? After you finish this placement, the question asks you, please determine the sum of the minimum value of the sum of the 4 numbers on the same face. The way you want to make sure the 3 numbers on the same face, the minimum should be greater than 10. And after you place this, the question says, how can you determine the minimum of the sum of the 4 numbers on the same face? Think about it. Okay, you pretty much do some enumeration and then do some guess out, figure out what it is, and then we'll see what we can do for this. Okay, let's go for a 10 minutes break, and then we'll resume after the break. And hopefully you guys can give me an answer after the break. Do we really have to go for the break, or we can just continue? Otherwise, I'm just gonna skip for the blank, and then we can go to like the solution part. Hey guys, are you there?
I don't think we need a break.
Okay, no more break, right? If no more break, let's jump to the solution. Okay? Yeah. I'll make it fairly quick, and then we can jump to our solution. Okay, it's here. Yeah, I see somebody already get a right answer. Okay, cool. So yeah, let's have a look. I see somebody that the right answer will be 16. 16 is the right answer. Okay, cool. I see some guys already got a right answer. So let's have an analysis first, okay? How we get a right answer. We need to have some analysis. So the first thing first, we need to do some observation, right? We need to observe the question. The question said, blah, 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 you have 8 numbers, place them randomly on the 8 vertex of a cube, such that for any given 3 numbers on the same face, the sum will be greater or equal to 10, right? That's the only tangible condition that we can do. Something, basically, you have a number greater or equal to 10. So please determine the minimum sum of the 4 numbers on the same face. Okay. Why 3 numbers? Why the total sum is greater or equal to 10? That's actually the million-dollar question you need to ask for yourself, right? That's the million-dollar question you need to ask for yourself. Why 10? Why 3 numbers? Just before we jump to the solution, these kind of questions, most of the time, you kind of basically do some analysis, find out some inequalities, right? Because you're trying to find out the minimum. And then when you have the right answer, the most important things is you want to make sure if you can really construct such a cube, which contains like the 8 vertices, really have the 8 different numbers. You need to find out in the reality if you can really see this or not, right? Just before we jump to there, let's have a quick observation. So let's say I already find such a face. I have A1, A2, A3, A4. 4 numbers on the face, right? Something is already there. According to the question, A1 plus A2 plus A3 will be greater or equal to 10, right? That's exactly given by the question. So your goal is pretty much trying to decide what is A1 plus A2 plus A3 plus A4 will be greater or equal to whatever. Something just like this. If I put them into the inequalities, you get something like this. Okay, so it looks like as long as I figure out the range for A4, I'll be ready to figure out the problem, right? I'll be able to figure out a problem.
Before we jump to the A4, let's do a quick observation for this guy. A1 plus A2 plus A3 must be greater or equal to 10. Who can tell me, based on this condition, is there any constraints for A1, A2, or A3? Who can give me some info based on this? Is there any constraint for A1, A2, A4? A1, A2, A3? They can be whatever they like to be? Or there must be a little bit criteria they need to follow to make sure their sum is greater or equal to 10? That's my question for you guys. Any ideas? Who can give me some ideas? A1, A2, A3 can be whatever. A1, A2, A3, these three numbers, their total sum is greater or equal to 10, right? So based on those information, is there any constraints for A1, A2, A3? Let's say A1, A2, A3 can be very small, or they can be too small. Something like this. Who can answer my question? Think about it. A1, A2, A3, they can be very small, like 1, 2, 3. Does it work? It doesn't work, right? So we need to find out something kind of okay. Maybe I'll just randomly ask them, guys, okay? Maybe 10 Maybe I'm going to jump off this bar. They can be too small.
Yeah, they can't be too small.
They can be too small, right?
Yeah.
So let's say A1, 1, 2, 3, it doesn't work out, right? A1, A2, A3, 1, 2, 3, their total sum won't be equal to 10, right? So who can tell me what is the at least one guy should be greater or equal to something? Right? Who can tell me this? Maybe Grace.
At least one of them has to be greater or equal to 5.
Is that right? You guys agree with Grace? At least one of them should be greater or equal to 5. If everyone is too small, 1, 2, 3, 4, add them together, it can't be more than 10 for sure. Right? At least you can have like something 1 or 2, it doesn't matter, but at least the one of them should be big enough. You have 1, 2, but the other one is 8 for sure. It pushes all the way to like what is that? To like 10, right? But at least one of them needs to be greater or equal to 5. That's a very good observation because these are based on the observation. We don't really go for like calculation. We just do some observation. So A1, A2, A3, at least one of them greater or equal to 5, right? Okay. If that being said, like I said, A1, A2, A3 are the smallest numbers on the face, right? The face, you have 4 numbers. A1, A2, A3 are the smallest number on the face. So that being said, A4 must be greater or equal to 6. Is that right? Because the smallest, you guys follow me? One of them is already more than 5. Because A1, A2, A3, I told you up front, they are the smallest number on the face. And the grids already help us analysis that one of them must be greater or equal to 5. I don't really care. But at least one of them greater or equal to 5. So that being said, whenever you choose A4, there's not too much options. Because the least 3 numbers already have one of them greater or equal to 5. A4, you can basically choose from 6, and that's it. Is that right? A4 must be greater or equal to 6. So you guys follow me? Yes or no? These are very important analysis. You don't really jump to the calculation or jump to the enumeration right away. Please do some analysis before you jump to the... So these are pretty intuitive. A4 must be greater or equal to 6. Okay, A1 plus A2 plus A3 greater or equal to 10. This is what I told you from day 1. A4 greater or equal to 6. So A1, A2, A4 greater or equal to 16. So a possible answer might be 16. I don't really know, right? Because this is inequality. Greater or equal to 16 not necessarily says 16 must be the answer for the question, right? Okay. So my question becomes, is it possible for me to construct such a cubic such that A1, A2, A3, A4, their sum is greater or equal to 16? Right? If I can find out a scenario, it's really greater or equal to 16, so my answer can be solved. Is that right? So we have two steps. Step number one, we do some kind of like rational analysis, some theoretical analysis. Step number two, let's do a trial to make sure after the trial and error, let me see if I really have such a cubic, can make sure the cubics have all the vertices and give me the more than 16. If 16 doesn't work, let's go for 17, right? I can't go for 15, right? 17, 18, all the way to whatever I can take it out. So who can tell me by what I said, 16, is there a possible scenario or not? Maybe I'm going to ask Andy. I see Andy has the right answer already. So can you tell me what I need to put for all my vertices for this? Two, you write that, huh? 2, 3, 5, 6. Exactly. So the one what I have here is 1, 4, 5, 6, 2, 8, 7. Okay, everything like this. So the face, what I'm talking about is actually this face, the little face on the right. Okay, you have like 5 numbers, you have 4 numbers, and the minimum of these guys are 2, 3, 5. Like Grace mentioned, the minimum cannot be lesser than 5. 5 is the minimum, and you can actually put another 6 here. And also, you place the other numbers on the other vertex to make sure you always make sure the sum of each face, the 3 numbers from each face, is greater or equal to 10. This is not a difficult question for sure, but it reflects some very important mathematical thinking. The mathematical thinking is that you need to do some hypothesis first. You solve your inequality, you solve your analysis, so on and so forth. And then, based on this, you're going to see if you can really find a scenario. If you finish your calculation, but you can never find a scenario, maybe your calculation is correct, but you can't find such a scenario, you need to push from 16 to 17, so on and so forth. So far, so good for the question? So far, so good? Okay. If all good, let's move on to the other question. Because every single question, we need to learn something. Okay? Another question. Number 5. This is a 2018 AMC question, number 14. Let's have a look to see how the question looks like. We have 3 guys, Joey, Chloe, and their daughter, Zoe. Okay? 3 names, Joey, Chloe, and Zoe. Okay? Follow the beat. All have the same verse. The same birthday. It's a family. Okay? The husband, the wife, and the daughter, they have the same birthday, but of course not born in the same year. Joey is 1 year older than Chloe. So the husband is 1 year older than the wife. And Zoe is exactly 1 year old today.
Okay, this is the baby. This is like 1 year old anniversary for the baby for today. Today is the first of the 9 birthdays on which Chloe's age will be an integral multiple of Zoe's age. What will be the sum of the 2 digits of Joey's age? It looks like a tongue twister. Zoe, Chloe, Joey. The next time his age is a multiple of Zoe's age. Just like one more thing before we move forward. Normally, like I said, every lecture we're going to ask one student to do a presentation. As presentation is one of the most important things we want to train for our lecture. So this is like the first lecture, of course, we have. So let's jump this to talking about the presentation. It's not a big deal. Okay. So let's jump from here. Like who is going to be the next? We're talking about the presentation, but it's not a big deal. Okay. Yeah, pretty much like a couple, and Joey, Chloe, Zoe, they have the same birthday, and today, Chloe, okay, yeah, Chloe is 1 year older. Joey is, you see, I'm also get confused, like like all the names, you can't use like some regular names, right? Why don't Chloe? So Joey is 1 year older than Chloe. The husband is 1 year older than the wife. And today, Zoe is exactly 1 year old. Today is the first of the 9 birthdays on which Chloe's age will be an integer multiple of Zoe's age. How do I understand this guy? This is kind of a little bit twisted idea, right? The twisted sentence we need to figure out. It means something like this. I'll give you an example. Let's say this is Chloe. This is Zoe, okay? Just give an example. Maybe today is 33. Zoe is like the first year, 1 year old, right? Of course, 33 is an integer multiple of what? So next year, the mother becomes 34. The daughter becomes 2 years old. Okay, 2 years old is also a multiple, right? And then next year, 35. He becomes 3 years old. 3 is not a divisor of 35. And then keep moving, the next year, 36, 4 years old, okay? So on and so forth. You go to a reasonable age, right? Less than 85, less than like 100, whatever. So there are only 9 times the mother's age can be a multiple of the daughter's age. Okay, this is pretty much what the question wants to say. Okay, so here comes the question. What will be the sum of the 2 digits of Joey's age the next time his age becomes a multiple of Zoe's age? So basically, what is the sum of the last 2 digits of the father's age the next time the father's age become a multiple of the daughter's age? So basically, you need to figure out what is going to be the next time the father's age become a multiple of the daughter's age, right? You got an age, you figure out what it is. So it's a little bit messy because all the names. Let me just write something from here. So again, we need to do some analysis. Observation, we are already done. This basically do the observation. We figure out what's the differences between the ages. So let's do a little bit of analysis before we jump to the solution. We always need to think about it before we jump to the solution. This is the father. This is the mother. This is the daughter. Let's say if the mother's age is X, father will be 1 year older than the mother, right? Today, their daughter is 1 year old, right? Let's say after several years, after 8 years, right? So mother will become X plus A, daughter will become 1 plus A, father will become X plus A plus 1, right? These are like the common sense. So we always start from the condition, right? This is a condition given by the problem. During the entire lifespan of the family, there will be only 9 birthdays, such that mother's age will be a multiple of the daughter's age. So that being said, this guy, when A changes, right? When A changes, X plus A will be divisible by 1 plus A for 9 times. All right? I didn't do anything. I just basically translate the human language into a kind of like a mathematical language. So this only happens for 9 times. Okay. This only happens for 9 times. It means what? I don't quite, maybe I can't really figure out for now, but let me think about it. So A plus 1 is the divisor by X plus A. Means X plus A, 1 minus A is an integer, right? For 9 times. For 9 times. Of course, when A is changing. How can I understand this problem? X plus A over 1 plus A. Here, A will become an integer. Excuse me. Here, A will become like a variable, right? When A is changing, this expression will yield an integer for 9 times. But for now, you know, the denominator and the numerator, they both have an A. It's kind of like a little bit confusing. Let me try to simplify a little bit. Simplify the expression a little bit. I'm going to put it at X minus 1, 1 plus A plus 1. I didn't do anything. I just want to make sure. I don't want to have the variable both in the denominator and also in the numerator. Right? It's kind of confusing. Let me try to a little bit simplification. I just get rid of it. Only have 1 in the denominator. So that being said, means this expression will yield 9 different integers, right? So that being said means X minus 1, 1 plus A will yield 9 different integers, right? Okay, X minus 1 over 1 plus A will yield 9 different integers. This is like a human language. How can I translate into a mathematics language? You see, this part I keep saying. X minus 1 over 1 plus A will yield 9 different integers. Of course, when A is changing, right? So what I keep saying is that you need to do a translation between the human language and mathematics language, right? So sometimes you need a human one, sometimes, or like most of the time you use like the mathematical one. So how to do this translation is actually something very important for the math competition. Okay, let's continue. So that being said, actually means X minus 1 must
have 9 different factors. Is it right? It can generate 9 different integers, of course, means it has 9 different factors. You see? We just basically change the problem from a human language into mathematics language. Okay. X minus 1 must have 9 different factors. So it means I need to find out a x minus 1 which has a different factor, 9 different factors. Which integer has 9 different factors? Which integer has 9 different factors? You still remember? I give you a hint. 36 has 9 different factors, right? We talked about it previously. 36 has what? 1, 2, 3, 4. Let me. 6, 9, 12, 18, 36. There are totally 9 different factors for 36. But people will say, how come you think about 36? For now, I give another number, they have 12 different integers. How can I do that? Yeah, of course. In the math competition, you cannot really guess out 36 right away. But don't forget, we just introduced the number of factors principle, right? The number of factors principle. If n can be written as P1, K1, P2, K2, all the way PL, KL. So the total number of the factors will be equal to what? K1 plus 1, K2 plus 1, KL plus 1, right? This is the number factor theorem we just introduced previously. Is that right? You guys still remember? Okay, so that being said, I need to find out the n, which I can put them into such a prime factorization scenario. And also I have K1 times K1 plus 1 times K2 plus 1 all the way times KL plus 1 equals to 9. So ideally, K1 will be equals to 2. K2 will be equals to 2, right? You can only find, because 9 equals to 3 times 3. You do a factorization, you find out you only have 2 terms, K1, 2, K2, 2. So that being said, your number must be a prime number to the power of 2, another prime number to the power of 2. Is that right? Here, P1, P2 are prime numbers. So what do you find for P1, P2? Prime numbers can be whatever, 2, 3, 5, 7, whatever, right? Looks like you still have infinitely many options. But don't forget, we're talking about the age, right? At this moment, normally people don't live more than 100 years old. In the future, I read a paper, say in about 50 years, people will be living forever. They already, like the genetic engineer already figured out we can kill like the caspase, in why people die, because there's a caspase, what is it called? I'm not an expert in biology. There's like a special gene, there's a special genetic mechanism in the cell. Like the cell, after it reproduce more than, I don't know, like 55 times or 25 times, it will stop. They will trigger the caspase procedure. The caspase procedure means that the cell, after reproduce a certain amount of time, will stop. It will basically go for 2 directions, either die or become a cancer cell. The cancer cell has no limitation. This can reproduce whatever times it likes. So that's like the caspase mechanism. So for now, people are trying to correct or modify the gene for the caspase process. So after a certain amount of time, people like this, like kind of a cell will continue reproduce while not becoming a cancer cell. So that being said, after 50 years, maybe like the question needs to be changed. Like we're gonna say not the age, but for now we're still good for like a less than 100. So think about it. Actually, it's only 2 or 3 can be there. 2 to the power of 2, 3 to the power of. As long as you have 5, That's got to be 25 times, and that's got to be more than 100. Is that good? So that being said, n must be equal to 2 to the power of 2, 3 to the power of 2, which is going to be 36. 36 means x minus 1 will be 36. Guys follow me? Because we're trying to find out the x minus 1 who has at least, not at least, exactly 9 factors. So now x minus 1 will be equal to the one we find out, aka 36. So therefore, x will be equal to 37. You see, something looks like totally untouchable, but basically you find it out directly by doing some enumeration and analysis. So therefore, using this number factor theorem is actually very important. In one of your assignment number 2, you will use exactly the same thing one more time. Okay? Okay, so that being said, we still have our Joey, Chloe, Zoe. X is already equal to 37. So that being said, for now, Chloe's age is 37. Father's age will be 38. Daughter's age will be 1. Right? But we're not there yet. We're trying to see, the question asks us to do what? We always need to remember where we came from. The question asks us to do, what will be the sum of the 2 digits of Joey's age the next time his age is a multiple of the daughter's age? For now, the father's age is 38. Daughter's age is 1. It's a multiple. But the question asks you, what about the next time? The next time it becomes another multiple. That's easy. Then after b years, it's exactly the same thing we did before, right? After b years, father's age becomes 38 plus b. Daughter's age becomes b plus 1. You want to make sure, you want to make sure 38 plus b over b plus 1 becomes an integer. Right? Of course, b as small as possible. Ask you the next time. It might have multiple times either. Just ask you for the next time. So that one is easy. We're using exactly the same methodology we introduced previously. We want to find out this number is an integer. But I have the b both on the denominator and in the numerator. It's kind of difficult. So let me just get rid of the one in the numerator. I just want to keep it in the denominator. So that one becomes 37 over b plus 1 minus 1. Right, just a quick rearrangement, becomes an integer. So the next one, you just do a quick thing. B will be equal to 36. Yeah, because 37 is a prime number. So the only thing can be divisible is b equals to 36. So it looks like there's only one chance to be the father's age being a multiple for the daughter's age. Not to say this time, there's only another time. Not like mother. The mother you have 9 times in total, while the father's age only have 1 number next time. So b will be equal to 36. It means after 36 years, the father's age will become 37 plus 30. Okay, let me say this. Let me change this. So that being said, after 37 years, father's age will become 74, right? For now, the father's age is 38 plus 36 goes to 74. And the daughter's age will become 37. That's a second time the father's age will be multiple of the daughter's age. So the question asks you, what will be the sum of the 2 digits? That will be 11. Okay? So this is an AMC question, but it's only question number 14. So it's still pretty much the Canadian level. So Euclid or like all the Canadian mathematician can go to the same level. So basically, it uses a very Okay, just give me a sec, because my screen is a little bit scrambling. So you guys can see my screen, right? No problem. Okay, so that actually use the basic technology we introduced during the lecture is how to determine the number of factors of a certain number. We always do this. We try to put a number into all the prime factorization and then calculate all the exponents. The exponents plus 1, times them together, you'll be able to determine what is the total number of factors of a certain number. That's for trick number 1. For trick number 2, we keep using in this question is that I want to say this guy is an integer. This guy is an integer. So basically, at the very beginning, it has the variables both in the numerator and the denominator. That's too much. So you need to get rid of them, at least for the denominator or for the numerator. It doesn't matter. Get rid of them. So as long as it goes to one form, you only have the variable either in one position, it's easy for you to do the analysis, right? 9 times multiple means the upper side, the numerator has 9 different factors. 10 times means 10 different factors. From there, you do some quick enumeration, you can figure out what is the exactly age for the father, right? And taking from there, you do the same trick once again. It's pretty much the same thing. You figure out the next time is going to be within 36 years. Okay, so let's do a quick recap. So in today's lecture, we actually introduced the basic concepts for the divisibility. So most of the divisibility related properties are pretty intuitive. You'll learn those for a long time. And one more thing is how to remember the number of the factors of a given number. So that one is important. It will be tested pretty much every time in the math competition. As long as you know this, you'll be able to try to solve the problem. Last thing is that in the future, we're going to see more problems in the number theory. Just bear in mind, number theory is very like to do factorization or divisibility or finding the factors, something like that. So most of the time, you do a multiple rather than add, because multiple is trying to find out the factors. So in the future, if you can do some factorization, try to do it. If you want to do some analysis, try to analyze them into a factors perspective, not into a sums perspective. We're getting there. We're going to give you more questions to train your this kind of what is called conditional react. Okay, this conditional react is going to help you eventually. So that's pretty much for today's lecture. You guys have any more questions? Yep. Any more questions for me? So hopefully, during the entire process, there's a lot of students asking me questions in the group chat. So privately, so as long as you have any questions, you can always ask me from there. Okay? So far, so good? Yes or no? Please give me some feedbacks, okay?
Yeah.
Okay, perfect. Thank you. Yeah, I know it's pretty much lunchtime. Excuse me. It's pretty much like the dinner time. We're kind of like running out of time because today we have some introductions from the very beginning, so we're kind of like delayed our schedule. But normally we should respect our schedule, make sure you go for dinner on time. All right. If that's the case, hopefully everyone you have you have a good understanding of today's lecture. So number theory won't be taught in the day lectures, day schools, but it will be required for the math competition to answer Ning's question. Yeah, that's pretty much the case because the day school doesn't require it, so it doesn't really teach it. Well, the number theory will be required for math competition, so you need to somehow figure out a way to bridge the gap. That's pretty much where our lecture comes from. All right, I think that's pretty much for today's lecture. Afterwards, I'm going to upload an assignment to our Google class. You guys will be looking at the assignment. Plus, I'm going to put a preview for tomorrow's lecture. All right, so hope you guys enjoy the rest of your day, and we'll talk to you guys later. Bye now.